Hello everyone. So in the last video we done the multiplication, and then we have seen how to do a multiplication of a matrix by a scalar, and we've done the traverse, the transposing of a matrix, in which you have rows and columns, and then you just convert those to so rows becomes columns and columns becomes rows. That's what transpose is all about. In the multiplication, however, when we done the scalar multiplication, so the scalar, you basically multiply the constants by each and every element within the matrix, and then actually I don't think I have it here, but you generally get the notion. However, when it comes to multiplication, we do what is called the dot product. The dot product, you generally have a vector, and then once you do a vector multiplication, you have a few things that you need to consider, and we will be looking at that later on in some video in the very near future, the dot products. But we have already looked at the multiplication of two matrices, and then we could actually do it's a bit complicated, and for that reason, well, not complicated in terms of the process, but it's more complicated visually to do. So what you have to do is have a row, and then you multiply it by a column. So once you have, for example, you have this process here. So if you've multiplied it by the first column, then it is the first element within the matrix. If it's the second column, then it is the second element within the matrix, and so on and so forth. So how is this done again? So 1, 2, 3. So you'll have 1 multiplied by 8, 2 multiplied by 10, and 3 multiplied by 12. And then you add all those together, and that's what you get, the 64. And generally speaking, if you have a 2 by 3 matrix, the end result would be a 2 by, so it is m multiplied by n multiplied, so m. So if it's 2 rows here, and then you have the 3 rows here, then the 3 rows has to conform with the columns on the first matrix we're multiplying by. There we've also we were also acquainted or introduced to the identity matrix, in which you have the diagonal being ones and the rest of it is a square, and the diagonal being all ones. Now, something to note here: the commutative property is not valid when you multiply matrices together. So A multiplied by B is not actually B multiplied by A. And there are also some other examples. Now, assume in this case A multiplied by B and B multiplied by A in this case, then what's the value of X? Then you would solve A by B, and then you would have B by A. You'll have two end results like so. So what you are going to do is that when you have the 1 plus X would equal to, so this here would actually equate to this matrix here. So 1 plus X would equal to 3. 1 plus 2X would equal X plus 3, and then you would also solve accordingly. And that's what we've seen with the multiplication. Now, the addition, we've already seen this before. You just add, so once you do the addition, you have each element, you add it to the next element, and then you have the end results. So each element by its own element, and the subtraction is actually the addition of a matrix multiplied by -1, and then you just do the addition as like we've seen. Now, what we decided to talk about in this video is called the inverse. Now, why is this important? Because this is important simply because once we do the multiplication, we will have to do what is called the division, and the division is not really possible without the multiplication. So the division is actually a multiplication of the matrix by its inverse. That was good. Not really by the inverse, but so if you have A multiplied by B, and then you have A divided by, and then you have an A divided by B. So what you would have to do is that you would have A multiplied by B inverse. That's how you generally do it. Okay, so the reciprocal of a number, let's you have an 8, that's an eighth, that's the inverse. And we have to prep ourselves to actually add some comments here. So we've done the multiplication, the commutative property, and then the inverse becomes 1/8 matrices. Then we do the inverse as follows, and that follows generally is what we will be studying now. The inverse of a matrix is the same idea, but we write it a to the power of -1. Okay, why not 1/a? Because we don't divide by a matrix. But anyway, when we multiply a matrix by an inverse, we get identity matrix. So this is important to us, right? We do this 8 when we multiply 8 by 1/8, we get 1. With matrices, we get the identity matrix. A to the power of -1. Okay. Matrix is the matrix equivalent of the number 1. Can be 2 or any other size for that matter. So I think we should actually copy this because this is a really important note, and we have to I think it's super important to have this note. Let's keep on going. How do we calculate the inverse? This is important. For a 2 by 2 matrix, the inverse is 1/AD minus BC. Okay. In other words, swap the positions of A and D, put negatives in front of B and C, and divide everything by the determinant. Let's try this. I'm not sure if it's for a 2 by 2. So this example, right here, copy it to where we need it. So when we have that, so it's like you have the x with the negative of this. Okay. Determinants. So we have 4, 7 to 6. So it's 4 multiplied by 6 minus 7 multiplied by 2, which is 14. And then you have 24 minus 14, that's a 10. And then you multiply this by each and every element within the matrix. So to know this is right, we multiply this. Is it a multiplication? Yeah, we multiply this by this, the way we do it, row by column, row by column, row by column, and row by column. You should get the identity matrix. And so 4 multiplied by 0.6 plus 7 multiplied by negative, and then you do the same here, plus this, and then this, plus this. We end up with the identity matrix, so it must be right. Why don't you go? Why don't you have a go at multiplying these? See if you get the identity matrix. I believe. Now remember, it's a multiplication of this, but I believe it shouldn't really matter, should it? Because yeah, because so it has to be sufficed for both. It has to be sufficed for both. Okay, we should have a go at it, I guess, so that we will be extra certain what we're doing is actually right. Here we have, so we have 0.6 multiplied by 4, and we have plus 0.6 multiplied by 4 plus, that's actually negative 0.7 multiplied by 0.4, and this should give us 2.12. This is interesting. Wait a second, so 0.6 multiplied by 4, that's 2.4, and 0.7 multiplied by 2, 1.4. So 2.4 minus 1.4 is actually 1. That's a 1. For the second row, 0.6 multiplied by 7, that's a 4.2. 0.7 multiplied by 6, that's 4.2. So we should get a 0 there. So that's an identity matrix as well. Now, why do we need an inverse? Because with matrices we don't divide. See, so there's no concept of dividing by a matrix. But we can multiply by an inverse, which achieves the same thing. Imagine we can divide by numbers. As someone asks, how do I share 10 apples with 2 people? We can take the reciprocal of 2, which is half. So we answer 10 multiplied by half to get 5 apples each. Can be done with matrices. Say we want to find matrix X, and we know matrix A and B. It would be nice to divide both sides by A, but remember, we can't divide. We want to find matrix X, but we know matrix A and B. But if we multiply both sides by A reciprocal, and we know that A is I, so we can remove I for the same reason we remove the 1 from our X. And we have our answer, so maybe we can divide it. Interesting, we should take this one in. So the identity matrix actually acts like the one coefficient for other matrices and for constants. But anyways, we should be able to the identity matrix. In that example, we're very careful to get the multiplications correct because with matrices, the order of multiplication matters. A multiplied by b is almost never equal to b multiplied by I. So the inverse is like the 1% train. A group took a trip on a bus at $3 per child and $3.20 per adult for a total of 118. They took the train back at $3.50 per child and $3.60 per adult for a total of 135. How many children? How many adults? So we've got the so first of all we've got the bus and the train. We've got two. Uh, then we have the end result, which is the total for bus, and we have the total for train. But we want to know how many adults and how many children. So that could be the children could be X and the adults could be Y. And then we will have to plot for the matrix the values for the bus and the values for the train. Um, and the price for each. Yeah, and we could also do it the way as could also do it the way we would usually do it with functions, right? Take a bus, a three per child, three bus per adult per bus. So we have um, for bus we've got two values, and we get the total. So the train X and Y. So to solve it, we need the inverse of X is unknown, we have A and B knowns. So we could do the inverse of A here to get rid of it, and then have B multiplied by I. So the reciprocal of this is this multiplied by this minus this multiplied by this, inversed and multiplied with M. Very inverse, right? Interesting. There were 16 children and 22 adults. Yeah, it almost appears like magic. It's based on good mathematics. By using much larger matrices to help engineers design buildings, using video games and computer animations to make things look three-dimensional in many other places. There's also associated linear equations, which we will have to solve linear equations. I think this is, yeah, it's not really talking about matrices yet. But usually what you would want to do, if we try to solve this like the traditional way, we would go like, so we have a bus, we have a bus, 3 per child and 3.2, so uh, multiplied by x would equal to 118. 3x, 320 adults equals 118. Yeah, so it's like x1 plus x20 equals 118, and 350 multiplied by the child x1, 360 multiplied by the adult y1, which goes on further, and we solve by substitution or elimination, either one. or we could just use the matrix to solve it. Say that we are trying to find x in this case. Order is important. This is different. This is different to the example above. X is now after a. It's not xa. Okay. With matrices, the order of multiplication usually changes the answer, noticing that AB equals B, no commutative property. So how do we solve this one? Using the method and we know that, okay, this is important to keep in mind. Why don't we try our Boston train example but with the data set up that way around? It can be done that way, but we must be careful how we set it up. So this is what it looks like. Ix equals B. It looks so neat. I think I prefer it like this. How the rows and columns are swapped over transposed compared to the previous example. Yes, it suffices the multiplication, I believe, isn't it? So if you have two rows, you have to have two rows here. Two columns, you have to have two rows. Not sure why was that the case though. To solve it, we need the inverse of A. Totally. It's like the inverse we got there, but transposed. Or swapped over. But why did you swap those over? Why did you? We need to solve this. No, wrong way. Okay, so I'll leave this to the next video in which we try to solve this differently and see if we can actually if we can solve this now instead of this being transposed. What if we try to solve it with it being, I'm not sure if that's possible, because if it's a single row then you have two columns, you have to have two rows, so this is the only way to do it. But what we want to do, what we want to try, is try using the normal method of solving problems, like have an equation with variables, with different variables, and solve accordingly. I think that's one way we should be. That's one way we should be after. Right. We could do the exercises as well in the later video. Inverse may not exist. Okay, so there's a possibility that the inverse may not exist. First of all, we have an inverse must be square. To have an inverse, the matrix must be square, same number of rows and columns. But also the term it cannot be zero, or we end up with dividing by zero. With this undefined, we cannot go any further. This matrix has no inverse. It's called singular. Which is undefined. think this is really nice. I liked how he was like, there's no new information. This is really nice. I like it when, when they say that mathematics is all about what is new. Lovely, isn't it? Anyways, we should do the exercises in the next video. I don't think there's anything other than that that's really important. So imagine our passenger example of the prices on the train were exactly 50% higher than the bus. So now we can't figure out any differences between adults and children. There needs to be something to set them apart. It's easy compared to larger matrices such as 3 by 3 and 4 by 4. Those larger matrices, there are three main methods to work out the inverse: elementary row operations, Gauss-Jordan. This is what we're looking for. Inverse of matrices in minus. Now we should cover all of these, but first we should do the exercises on the inverses, and then we should go to Gauss-Jordan. Alright, thank you for tuning in. Have a good day.